Hi all, welcome to another video of the subject DC machines and transformers based on the KTU syllabus, and we are on module 4, and today we are going to discuss the phasor diagram for an ideal transformer on load. So before going to the phasor diagram, we must know what happens when a load is connected at the secondary of a transformer. Okay. So when the secondary circuit of a transformer is completed through a load, we can say it as through an impedance, the transformer is said to be loaded and current flows through the secondary. Okay, and the magnitude of phase of secondary current I2, okay, this current I2 will be in phase and lag behind and lead the terminal voltage V2 respectively based on the load we are connecting here. Okay, that is, if you are connecting a resistive load here, the V2 and I2 will be in phase. Okay, and instead of that, if you are connecting an inductive load here, the I2 will lag behind V2. Okay, and if you are connecting a capacitive load here, the I2 will lead the secondary voltage V2. Okay, so that's the three cases here. So when the we have already learned that when the transformer is on no load, okay, if there is no, we are not connecting any load here, it draws a no load current I0. Okay, it draws a no load current I0 from the supply mains. That is to compensate for the core loss and the small copper loss, and also for the production of the flux, that is in terms of magnetizing current. Okay, so a small current I0 will draw from the supply mains. Okay, so this no load MMF, okay, this no load current I0 sets up an MMF N1 into I0. Okay, it sets up an MMF N1 into I0, which produces a flux phi in this core. Okay, flux phi here. So we know that the magnetic motive force is the cause for the production of the flux. Okay, so here, due to the current I0, okay, we are considering the previous case, that is a no load case, that is a small current I0 is flowing here. Okay, so due to that, an N1 into I0 current, okay, an MMF will be there, which produces a flux phi. Okay, so when an impedance is connected across the secondary terminals here, okay, a current I2 flows through the secondary. We know that a current I2 will flow through the secondary winding. So this secondary current I2 sets up its own MMF and hence creates a secondary flux phi 2 here. Okay, so due to this current I2, that is, if you are connecting, okay, listen carefully, if you are connecting a load here, this current I2 will sets up its own MMF in the secondary and it produces a flux phi 2 here. Okay, it produces a flux phi 2. That flux phi 2 will opposes the main flux phi here due to the according to the Lenz's law. Okay, so as per we have already discussed this flux phi. Okay, this flux phi is generated due to the current I0, and if you are connecting a load in the secondary, due to that current I2, it sets up a flux phi 2 here, and this flux will opposes the main flux phi. Then what happens? The effective main flux will reduce. Okay, the flux phi will reduce. So when this flux phi reduces, we know that the induced EMF E1, okay, induced EMF in the primary E1 will be reduces. Okay, so when this flux reduces, E1 will be reduces. So the difference between this V1 and E1 will increase. Okay, difference between V1 and E1 will increase. So when that difference increases, more current, we know that when the potential difference is high, that is in between V1 and E1, more current will drawn from the supply. Okay, so more current will drawn from supply by the primary. Okay, so that is the effect mainly happening here. Okay, so it will continue to draw that current until the main flux phi reaches. Okay, so when more current drawn from the supply, it will increase the induced EMF E1. Okay, it will again induce the increase the induced EMF E1 and will keep up a balance between this V1 and E1. Okay, so let us assume the additional primary current drawn here is I1 dash. Okay, previously a small current I0 only drawn from supply. So when we have connected the load, due to the effect of load, an additional current I1 dash, so here what is the main cause of this additional current I1 dash? So it is the current flowing through the secondary. Okay, when the current in the secondary began to flow, that is I2 is there. Due to that I2, a flux phi 2 is creating here. Okay, its own flux, it's the current I2 sets up its own flux phi 2. It will opposes the main flux phi, and due to that the main flux reduces. When this flux phi reduces, induced EMF E1 reduces. So the difference between V1 and E1 increases. So more current will drawn from supply. That excess current we are treating it as I1 dash. Okay, so the main cause of I1 dash is the current I2. So we can say that this I1 dash, okay, is in phase opposition with the secondary current I2 and is called counterbalancing current. I1 dash is called counterbalancing current. Okay, so this additional current I1 dash sets its own MMF N1 into I1 dash. Okay, N1 into I1 dash, which produces additional flux phi 1 dash. Okay, phi 1 dash in the same direction as that of the main flux phi, and which cancels the flux phi 2 in the secondary. Okay, so we can say that the MMF, okay, the MMFs N1 into I1 dash, okay, that is the MMF produced by the current I1 dash will be equal to N2 into I2. Okay, so due to the current I2 only, the I1 dash is producing here, so it will cancel each other. Okay, the additional MMF cancels the effect of the secondary current here. Okay, so we can equate them together, and from that we will get the equation for I1 dash as N2 by N1 into I2. This N2 by N1 we can call it as the transformation ratio. Normally we will denote it using the letter K, and it is K into I2. So I1 dash will be equal to K into I2. Okay, and if we can neglect the no load current I0, okay, that is compared to this I1 dash, the no load current here I0 compared to this I1 dash, no load current I0 will be very, very less. So we can, in some cases we can neglect that. Okay, so in that case we can easily compare, we can write it as the I1, this I1 dash will be equal to I1, we can treat it as I1. Okay, we can treat it as I1. So we can write as I1 is equal to I1 dash is equal to, okay, N2 by N1 into I2, that is equal to K into I2. Okay, so this is the basics of a transformer on load. Okay, so here, since the secondary flux phi 2 produced by the secondary MMF N2 into I2 is actually neutralized by, okay, is actually neutralized by the additional flux phi1 dash, okay, produced due to the current I1 dash in the primary. Okay, so the flux in the transformer core remains almost constant from no load to full load. Okay, so that's the main point you have to note down. That is, in the case of a transformer, the flux, okay, flux will remain constant from no load to full load. That is, if we are varying from no load to full load. Okay, so that's the one point you have to note down, and based on that we can draw the phasor diagram. Okay, phasor diagram. So always for drawing the phasor diagram, first we are considering it is a pure resistive load. We are connecting a pure resistive load here. Okay, so based on that we are drawing the phasor diagram first. So initially for a phasor diagram, we know that the x-axis we are having the flux phi. Okay, and we know that in phase with the flux we are having the magnetizing current Im, and in quadrature opposite, in quadrature axis, we are having the energy component IE, and the resultant will be I0. We have already learned in the previous lectures. Okay, so if we are drawing that here, okay, we can draw this Im here and IE here, and the resultant we can draw this I0. Okay, actually that's the case. So in the complex phasor diagrams we will not draw this Im and IE. Okay, so instead of that we will draw a small I0. Okay, a small I0 at a particular angle. Okay, at a particular 78 to 85 degree angle. Okay, we can eliminate this Im and IE. It is understood the resultant of this Im and IE will be I0. It is understood. So in some cases we may not, in complex cases we may not draw this Im and IE. Okay, so here we can draw the I0 only. Okay, we can draw the I0 only. That is flux, the flux phi is here, and we are drawing a small current I0, no load current I0 here. This is I0. Okay, and we know that the induced EMF E1, okay, induced EMF E1 is 90 degree lagging. Okay, with the flux phi we have already learned that E1, we will draw the E1 here. Okay, and the primary voltage V1 will be exact opposite with this E1. That is, here we can draw V1 which is equal to minus E1, okay, and the secondary, okay, and the secondary voltages, okay, secondary induced EMF V2 and secondary voltages V2 are also in phase with E1. Okay, that also we have learned in the previous lectures. That is, V2 will be equal to E2 here. Okay, and here we are considering the load as a pure resistive load. Okay, pure resistive load. So the current I2, okay, the current I2 will be in phase, okay, will be in phase with the voltage V2. Okay, current I2 will be in phase with the voltage V2. So we can draw the I2 here. Okay, and we know that the additional current I1 dash, okay, I1 dash is in exact phase opposition with the I2. Okay, so we can draw that I1 dash here. Okay, and the primary current I1, okay, the primary current I1 will be the vector sum of this I0 and I1 dash. Okay, so we can draw that here. Okay, the vector sum, we can draw the vector sum like that using the parallelogram law. So this will be our I1. Okay, so this is the phasor diagram of a transformer with pure resistive load. Okay, it is very easy to understand. The points you have to note down here is Okay, the current I1 dash, additional current I1 dash will be always will be in phase opposition with I2. Okay, and also we are drawing this I2 in phase with the voltage V2 here, because it is an pure resistive load. Okay, pure resistive load. So because of that, we will draw the I1 dash in exact opposition with the I2, and I2 is in phase V2. Okay, a resultant of I0 and I1 dash will be I1. So that is the case of a phase diagram of for an ideal transformer on load. Okay, so with that we are winding up this video, and we will discuss the phase diagram for the transformer on inductive and capacitive load in the next video. So thank you.